everybody! Today we are going to learn the new content, solubility of the precipitate. We know precipitation titration and precipitation gravimetry are based on the precipitation reaction. So, in order to ensure the accuracy, the precipitation reaction is required to be as complete as possible. The degree of precipitation reaction is usually determined by the solubility of precipitates. The smaller the solubility, the smaller the experimental error caused by the dissolution of the precipitate. Then, what's the solubility of precipitate? What are the factors affecting the solubility? We know that when sparingly soluble ionic compound Ma is dissociated in water and reaches saturation state, it will have set equilibrium. That is, the dissolved part of the solid Ma includes the existence of ion state M and A, and the molecular state Ma, which is not dissociated. Of course, it can also be the ion pair Ma. In saturated solution, the equilibrium constant K relative to Ma molecule at liquid and solid state is equal to division of the activity of the liquid molecule, Ma, by that of the solid molecule, Ma. Since the activity of the solid molecule, Ma, is 1, the activity coefficient of the liquid molecule, Ma, is 1. The equilibrium constant K is equal to the equilibrium concentration of the liquid molecule, Ma. At a specific temperature, the concentration of the liquid molecule, Ma, in the solution is a constant, and it is called the molecular solubility of sparingly soluble compound, also known as the intrinsic solubility, which is usually expressed as S0. So S0 is equal to the equilibrium constant K. For the sparingly soluble compound Ma, if we ignore the side reactions present in the solution, that is, the ideal state, the solubility S of Ma is equal to the sum of the intrinsic solubility S0 and the equilibrium concentration of M or A. Considering that most of their intrinsic solubility is relatively small, the molecular form or ion pairs can be ignored. Therefore, the solubility of the precipitate Ma can be directly expressed by equilibrium concentration of M or A. However, there are precipitates with high intrinsic solubility S0, such as the saturated solution mercurous chloride, whose dissolved part mainly consists mercurous chloride molecule, only a small amount of mercurous and chloride. In this case, the intrinsic solubility S0 should be considered when calculating the solubility of the precipitate mercurous chloride. Otherwise, the error will be very large. Under ideal conditions, the solubility S is equal to the equilibrium concentration of M or A for most sparingly soluble compounds. Then, how to calculate the equilibrium concentration of M or A? In order to find out their equilibrium concentration, we need to resort to the activity product or solubility product. With the equilibrium relationship of Ma in aqueous solution, it can be obtained as follows. The activity coefficient in the activity product constant can be replaced by the product of the activity coefficient and the equilibrium concentration. It can be found that there is such a relationship between the activity product constant Kap and the solubility product constant Ksp. The activity product constant is normally only related to temperature. However, the solubility product constant is not only related to the temperature, but also ionic strength of the solution. In the Manual of Analytical Chemistry, we can check out the activity product constant, Kap, of sparingly soluble precipitates. Generally, their solubility is very small, as well as the ionic strength. Therefore, the effect of the ionic strength I is not considered, and the Ksp can be used instead of the Kap. Only when the ionic strength of the solution is very large, the influence of ionic strength is taken into account. Then, according to the calculation formula of the solubility product, for the 1:1 precipitate Ma, Ksp equals the equilibrium concentration of M times A, and equilibrium concentration of M equals A in dissociation equilibrium. So Ksp equals square of equilibrium concentration of M equals to square of equilibrium concentration of A. The solubility S of Ma can be expressed as and for the M2N precipitate, so the solubility S of Ma should be calculated as follows. For example, the solubility S of calcium phosphate is equal to the aforementioned calculations of solubility are all obtained on the premise that the dissolved Ma only exists in the state of Ma molecule M and A, without any side reactions. In practical situation, the precipitation equilibrium is more complex and easily affected by the side reaction. So, how to calculate the solubility in the presence of side reactions? If you want to know the answer, please follow the next class.